All right, last topic of this unit, gas stoichiometry. So I'm kind of feeling like Justin, Timberlake here, right? I'm bringing stoichiometry back. Well, we got to deal with it. So we have that part of our flux capacitor, and I'm only going to draw one part of it, where we had moles and we had liters of gas over here, right? And I told you, kind of put it away for another day, right? Well, that another day is here now. So to go from moles to liters of gas, it is a constant. There's 22.4 liters of any gas in a mole of it. Likewise, 22.4 liters of a gas in a mole. So if you want to go this direction, you're dividing moles to liters, you're multiplying. And we're going to use that along with all of the principles of stoichiometry that we have done. Now remember, we have to analyze now, when we look at equations, what the substances are. Are they solids? Are they liquids? Are they gases? Are they aqueous? Etc. So the first problem that we have here, let's do it together. It says we have acetylene burning in oxygen to make water and carbon dioxide. So it's a combustion reaction where we have C2H2, acetylene, reacting with O2 to create CO2 and H2O. You know I like to write that as HOH. Well, the first thing I got to do on any equation is balance it, right? So I'm going to go ahead and balance this chemical equation. So let's go ahead and do that. So when we balance this, it goes 2, 5, 2, and 4. I'm cheating, but I want to be able to get to the substance of the problem. We should be able to do that by now. Okay, so now continuing along. It says if you have a 10-liter tank of acetylene, so we have 10 liters of this gas, acetylene, at 25 degrees Celsius and 100 atms of pressure, how many liters of this? Oh, so we give you this, we ask you this. That's why it's stoichiometry. Dun, dun, dun. And that's what should tip you off, is if I ask you one thing, or give you one thing, give you another, and they're gases, then it becomes a gas stoichiometry problem. So, Pugner equation for acetylene is as follows. PV equals nRT. That was the first thing I did. So I said, okay, we say it's 100 ATMs, and that's a decimal place, 3 significant figures. The volume was 10.0 liters, 3 significant figures. What we're solving for is N. We want to know how many moles of C2H2 times 0.08205 liters ATMs per mole Kelvin, right? The R constant, times the temperature, we just told you, is 25.0, which becomes 298.15 Kelvin. Why? Because Kelvin's got to match Kelvin. ATM's got to match ATMs. Liters to liters leave us moles. We get the N, and that N is equal to 3 sig figs, 3 sig figs, 4, 5, 3 sig figs, 40.9. Now, what is that moles of? It's moles of C2H2. Well, guys, that's not what I asked you for. I want to know how much of this we're making. So now we're going to take 40.9 moles of C2H2, and using the balanced chemical equation and stoichiometry, we're going to convert. So here's your mole ratio. How many moles of C2H2 for how many moles of CO2? Well, we go to the balanced chemical equation. There is a 2 here. So 2, that 2 is right there. And for CO2, there are also 2 of them. Now in this problem, you are also asked for, let's see. Oh guys, you know what? I flipped this. I apologize. This is a 4. This is a 2. Yeah, okay? I got a little sloppy for a second. So that changes these numbers. Still makes this a 2, but this one is a 4. Boy, that would have been a big mistake for me. Glad I caught it. So, the answer wants to know what it is in liters. Well, that's where this comes in. In 1 mole of any gas, there's 22.4 liters. Therefore, in 1 mole of CO2, 22.4 liters of CO2. Moles cancels moles, moles cancels moles. Leaving us liters of CO2, that's what we want, equals. You start with 3 stiff figures. When we do stoichiometry problems, we always end with what we started. So, the answer, therefore, is, I get 1832 liters, but we can only have 3 sig figs, so 1,830 liters. Now, if you gave me 1,832 liters, I'd probably give you a 9 out of 10. You know how to do a gas stoichiometry problem. All right? I'd be more concerned about that than I would necessarily, the sig figs piece. But this is the correct significant figure answer. Let's go ahead and do another one. Number 2. Then I'm going to set you free. So number 2. Number 2 says you have CaCO3, calcium carbonate, and that is a solid decomposing into carbon dioxide gas plus CaO solid. How many grams of calcium carbonate, so how many grams of this, to form 3.45 liters of this, a gas? So here's what you do. You start with 3.45 liters of CO2. And we said it's a gas, right? So therefore, if there's 22.4 liters of gas in a mole, we can do that. We then have moles of carbon dioxide, don't we? Which brings us to our most important step, mole ratio. So, to compare moles of CO2 to moles of CaCO3, right? Because we want to know that. Well, we go find the balanced chemical equation. By the way, this was balanced, that's why I did it. It's 1, 1, 1, 1, 1 Ca, 1 Ca, 1 C, 1 C, 3 O's, 2 plus 1 is 3 O's. So, the balance is 1 over 1. There's a 1 there, that's there, and a 1 that is here, that is there. Last thing is this then. In 1 mole of CaCO3, well, I want to know this in grams, don't I? I can calculate the molar mass of CaCO3, can't I? From the periodic table. Calcium plus carbon plus 3 oxygens. When you do that, you get 100.09. Remember, we round those things to the hundredths place. And again, it's just the molar mass. There's 100.09 grams in 1 mole of CaCO3. We did that a lot before. Well, we do the math. We multiply tops across. We multiply the bottoms across. We had 3 significant figures when we started. Therefore, we're going to finish with 3 significant figures. The answer is 15.4 grams CaCO3. That's gas stoichiometry. We did a couple of problems. Now it's time for you to do some.